Okay, the next section, just moving along in the textbook to 7.5, is over indeterminate forms and something called L'Hopital's rule. And I'll explain what both of those are as we go along. The first one, indeterminate forms, they are expressions like these. So 0 over 0. We know we can't divide by 0, so this doesn't actually mean anything. That's why it's called an indeterminate form. And there's quite a few others that you might run across in calculus, like infinity over infinity, or infinity times 0, or perhaps 1 to the infinity power, or even 0 to the 0 power. And one more. You might see infinity minus infinity. And you probably run across a few of these in Calculus 1 when you were doing limits. But the thing about all of these expressions is that they look like numbers, but they aren't actually numbers. So you might remember that infinity, even though we often want to think of it as a number, is more like a behavior or a concept. Infinity is like the concept of being never ending or going on forever. So we can't really treat it like a number. We can't divide by infinity. We can't multiply by infinity. We can't subtract infinities. So these things look like numbers, but aren't. And these come up, I believe I mentioned, they come up pretty often when you're doing limits. Like this example here. We can consider what happens if you try to take the limit of this function, f of x equals sine x over x, at x equals 0. So normally what we would do is set up the limit. Like this. And you probably remember that both of these functions are continuous. They're smooth. We can draw them without picking up our writing utensil. And since they're continuous, we should be able to just plug in x equals 0. So if you do that, what you would get is sine of 0 over 0. And there's already a problem here. There's a 0 in the denominator. But sine of 0, if you remember on the unit circle, just a quick little reminder, on the unit circle, 0 is over here, and we're looking at the y-coordinate. So this is 0 over 0. So this particular limit is one of these indeterminate forms, even though this function, sine x over x, appears like it should be a fairly simple function that we can deal with in calculus. But we end up with these limits that are indeterminate. And we need a strategy for dealing with them. Here's another little example. So if this was example 1, here's another one. So you might remember the definition of a derivative also involved an indeterminate form because it looks like this. It's the limit as h goes to 0 of whatever function you're looking at. I'll call it f. So f, and you plug in x plus h, and then you subtract f of x and divide by h. And this is also a 0 over 0 indeterminate form, because if you plug in 0 for h, so if you put a 0 in here and down here in the denominator, what you'll end up with is f of x minus f of x. That's a 0 up top, and then another 0 on the bottom. So this is what we might call a 0 over 0 indeterminate form. So thinking back to your Calculus 1 class, what did you usually have to do if you were trying to find a derivative by hand, like this, using the definition? What was your strategy? Anyone remember?
Isn't it like taking the first derivative or something?
Right, so this is the definition of the derivative.
Don't you factor out the h after you've done all your algebra?
Right, so your goal here is to try to factor an h out of the denominator, or sorry, this is the numerator. You're trying to factor an h out of the numerator so that you can cancel it with the h in the denominator. Good. So that was our strategy in Calculus 1. And you might remember finding some other limits where you could do some cancellation and then you're able to find the limit in the end. Those involved things like polynomials. But when we have more complicated functions like sin x in the numerator or the denominator, it's a little bit harder, or quite a bit harder really, to try to find something that cancels out. Sometimes there are ways to do it, but most often it's not clear what to do. So let's put a line here since things are getting crowded. So instead of trying to cancel something out in something like a trig function where it might not even be possible, what we're going to use is something called L'Hopital's rule. And well, the statement of it is a little bit dense at first, but once you've done it a few times, it should be clear what to do. And I think someone's microphone is open. If you guys can double check that you're muted, that would be good. Okay, so what does L'Hopital's rule tell us? It says that, first of all, I need two functions where when I plug in some number, they're both equal to 0. So think of these two examples. If you plug in x equals 0, then both of these functions are equal to 0. That's the setup here. And there's a little bit more. I need to be sure that my functions are actually differentiable. So this means they have a derivative, in case you've forgotten. or if that term is unfamiliar. So they need a derivative on some interval containing a point. We won't stress this too much. And we also need to know that the derivative of the second function g is not equal to 0 if we plug in a. Let's see. Caleb, could you mute your microphone? Thank you. There's a little bit of background noise coming in, I think. Okay, so that setup, like I said, it seems complicated, but here's the punchline. So this tells us that if we come across a limit like this, and going back, if we plug in a in the top and the bottom, that means we would get a 0 over 0. So this is actually a 0 over 0 indeterminate form. But what this theorem is going to let us do is replace this indeterminate limit with a new one. And all you're going to do is take the derivative of the top and the bottom, like so. Okay, so let's go back to that first example, just so we can be sure that we understand the theorem. So this was the limit as x goes to 0 of sine x over x. And let's just make sure that we double check that all of the things up here, the requirements of the theorem, are satisfied. We know that when we plug in 0, let's see, I need some more room here. So we're checking the conditions of the theorem. Or of L'Hopital's rule. So we know that sine of x, if we plug in 0, is 0. And we know that, well, if we plug in 0 here, need some more notation. Let's just label these f and g. Then g of x, the denominator, is 0. And we also know that the two functions are differentiable. We know that the derivative of sine is cosine. We know that the derivative of g is 1. Okay, so that means since we've checked that all of these conditions of the theorem are true, that means we can actually use this formula. So in order to do this indeterminate limit, what I can do is replace both of these functions with their derivatives. So I already wrote down the derivatives here. We get a cosine x and then a 1 from f prime and g prime. Is this an indeterminate form, or can I plug in my limit since both of these are continuous?
No, it's 1.
Right, it's just 1 now. Now we can plug in x equals 0. And we know cosine of 0 is 1. And since we're dividing by 1, we get a 1 overall. Good. Any questions so far? Okay. Now we're going to do lots of examples to make sure we have a good idea of what's going on. So first of all, we know that this is continuous, and we know that the stuff down here is continuous. Maybe I should mention, this isn't something that we stressed in the lecture, but both exponential functions and logarithms are continuous. So we should be able to just plug in 1 in this limit. I didn't stress this in class, but you might remember we drew graphs for all of these kinds of functions, or I used the computer to produce graphs, and we could see that they were smooth functions. And I need to go mute that. Okay, sorry about that. So we should be able to plug in 1. We know that exponential and logs and sines and polynomials, all of those are smooth when we graph them. That's what we mean by continuous. But there's a problem. What happens when we plug in 1 up top? Anyone?
You get a 0.
You get a 0. What about the denominator? What's log of 1?
1.
So is the natural log of 1 equal to 1?
Yes.
So you might want to think back to maybe your pre-calculus or algebra class. Remember, logarithms, you're trying to figure out what power of e is equal to 1.
It's 0.
It's 0, right. So the natural log of 1 is actually 0. What is sine of pi?
negative. No, it's 0.
It's 0, right? So think back to the unit circle. If you're ever in doubt, pi is over here on the left, and we're looking for the vertical coordinate since we have a sign. So that one's a 0. So this limit is a 0 over 0 indeterminate form. Do we know how to take derivatives of the top and the bottom using what we know? Can you find a derivative for x minus 1?
Yeah.
Can you find a derivative for this one? It's more complicated, but log x minus sine pi x? Would you know how to find a derivative of the denominator? No one wants to commit to being able to find a derivative. But using the rules that we know, we talked about how to find the derivative of the natural log. And you know from calculus 1 how to take derivatives of sine. And this one just has an extra constant multiple in sine of it. We can add an extra set of parentheses to show that. But we do know how to find the derivatives, and we know this is a 0 over 0. So L'Hopital's rule applies. Let's see. Just write it up here. Okay, and it's pretty important that you double check before you use L'Hopital's rule that it actually applies. Because if you have something that's not of this form, 0 over 0, then it might not work. And you'll probably see some examples of that on your homework. I don't think I brought any here on my note sheet because there's lots of skills that we have to practice where it actually does apply. So what's the derivative of x minus 1?
1.
It's 1. What's the derivative of log x, natural log of x?
One over x.
Right. So this is one of our new rules from, I guess, last week. What's the derivative of sine pi x?
Is it pi cosine pi x?
Pi cosine pi x, good. So the extra pi in the front comes from the chain rule. The inner derivative of this guy is the constant pi. And then the outer derivative gives you the cosine. Okay, so now what happens? If you plug in 1, are we allowed to do that now? So up top, we'll definitely get 1. Down here, we'll get a 1 over 1. That's fine. What's cosine of pi times 1? Just cosine of pi.
-1.
It's minus 1, right. So we can actually plug in 1 at this point, and we'll get this, 1 over 1, and then, let's see, I guess I'll just write all of it out. Minus pi times minus 1. So you can sort through how this simplifies. There's a couple minus signs. 1 over 1 is just 1. So we get 1 over 1 plus pi. Any questions over that example? Okay, so then let's do the next one. So first of all, do we need L'Hopital's rule on this problem? Let's double check. If you plug in 0, that's where we're taking the limit now, you get 0 minus sine of 0 over 0 squared. Sine of 0, that's over here on the unit circle, is 0. So you do get a 0 over 0. And we also know how to find derivatives of the top and the bottom. So L'Hopital's rule applies. Okay, so we've checked that. Now the next step is to just use the rule. So we'll replace this limit that we can't do with a new limit where we take the derivative of the numerator. What's the derivative of the numerator? The top?
1 minus cosine of x.
Good. 1 minus cosine x. What's the derivative of the denominator, x squared?
2x.
2x, right. Okay, and we're still looking at continuous functions. We know the trig functions, the simple ones like sine and cosine are continuous. This is definitely continuous. So we should be able to plug in x equals 0. So let's check. 1 minus cosine of 0 over 2 times 0. Well, there's a problem. We're dividing by 0. But what about the top of our fraction, the numerator? What's cosine of 0 again?
1.
It's 1. So we're looking at another 0 over 0 indeterminate form. So even though we've already done L'Hopital's rule, we still have another indeterminate form. So we have to do L'Hopital's rule again. So it's perfectly fine to use L'Hopital's rule any number of times, as long as that you check that it actually works. So as long as you're actually looking at an indeterminate form. So we do more derivatives. We take the derivative of the top again. What do we get? What's the derivative of 1 minus cosine x?
Sine x.
Sine x. What's the derivative of 2x?
2.
2. Good. So now we're dividing by 2. We're definitely not going to get an indeterminate form at this point. So we know that we're done with L'Hopital's rule, and all we have to do now is plug in x equals 0. What is sine of 0?
0.
Right, it's 0. And 0 divided by 2 is equal to 0. Okay, any questions before we move on? Okay. So the next thing that we need to know is that L'Hopital's rule, the one that we've been using, also applies to one-sided limits, like this one. The limit as x goes to 0 from the positive side, from the right, of sine x over x squared. So are we looking at an indeterminate form? Well, maybe let me write that. This is a right-hand limit, in case you've forgotten what the notation means. Okay, so sine of 0 is 0. X squared at 0 is also 0. So this is a 0 over 0 indeterminate form. So since we know L'Hopital's rule applies to one-sided limits, and we have an indeterminate form where it applies, then we can just take the derivative of the top and the bottom and go about our business. Okay, so we've seen these functions already today. The derivative of sine is, of course, cosine, and the derivative of x squared is 2x. And at this point, we have to be careful, I guess, because we get not a 0 over 0 indeterminate form. We're actually looking at a 1 over 0 kind of situation, because cosine is 1 when you plug in 0. And if you plug in 0 in the denominator, then we get a 0. Does anyone remember what happens when you get something like this in a limit?
It's undefined.
It's undefined. That's right. But this is also where the idea of infinity comes in. Because we're dividing, in this case, a number that we get out of cosine by a number that's getting smaller and smaller. And when we divide something by something getting smaller and smaller, that means it's going to get bigger and bigger. But of course, saying that in words doesn't give you a good picture. Let's pull up a graphing tool. Okay. switch the screen over. Okay, so here I'm going to Desmos. And let's just take a look at this function, y equals, let's see, I guess this will work automatically if I just type a fraction. Sine x over x squared. Here we go. So we're doing a right-hand limit. So we're coming in from this side on the right, and we're trying to find the limit as x goes to 0. And we saw in our calculation over here on the paper that if we use L'Hopital's rule, we're going to get something like 1 over 0. And since we're coming in from the right, this 2x is always going to be positive. This might be a little bit small for you, but I'm just going to write it down here. This is positive since we're coming in from the positive side. And we know that cosine on this side of the circle near 0 is also going to be positive. So we're going to get a positive limit since we have two positive numbers, but it's blowing up to infinity because we're trying to essentially divide by 0. And we can see that playing out on the graph visually. As we come in from the right, we get this vertical asymptote here as x goes to infinity. We can zoom out and see this function really just blows up, goes vertical. So while we're here looking at the graph, you should also pay attention to what happens on the left-hand side. So if we come from the negative side, it looks like we're going to get a negative infinity since this is going straight down to negative infinity. I'm going to close this down, and then we should work through by hand the math of what's going on, because that's also a limit that works similarly to this one, because it's a 0 over 0 still, indeterminate form. So we can replace it with the same function that we did before, the derivatives of the numerator and the denominator. But now things are going to work a little bit differently. We're still looking at a 1 over 0 kind of form. But now the numerator is positive. Remember to think back to the unit circle. Over here, the x coordinates are all positive. So cosine is positive. But since we're coming in from the left side, now 2x, we're plugging in, or thinking of plugging in negative numbers for x. So the denominator is going to be negative. And this is what we saw playing out on the graph. When we divide a positive by a negative, we get a negative number, but we're also dividing by smaller and smaller numbers, so this is going to blow up to infinity. And in this case, negative infinity. Are there any questions over that idea? Okay, so let's look at some more kinds of limits. So L'Hopital's rule applies to 0 over 0 indeterminate forms. It applies to left-hand and right-hand limits, and it's also going to apply to infinity over infinity indeterminate forms, like this one. We know from our experience in the last few sections that the natural log of x just keeps on getting larger and larger as we plug in larger numbers. And we already know that the square root of x function also just keeps on getting larger and larger as we plug in larger numbers, like here in the limit. So this is one of these infinity over infinity indeterminate forms. And since I have Desmos already open, maybe we can just graph those functions. So the natural log, remember, looks like this. So it just keeps on getting bigger as you go to the right. It doesn't get big very fast, but it keeps on getting bigger. And then the square root function, or 2 times the square root function. Oops. Also keeps on getting bigger as you scroll over to the right, or if you zoom out. So this is a 0 over 0 indeterminate form. And we can use L'Hopital's rule on these. Okay, so the derivative of the natural log is 1 over x. And remember, this square root, this is actually x to the 1/2. Let's see. Let's find some space down here. The square root of x is x to the 1/2 power. So we're going to be using the power rule on this guy. So that's 2 and then 1/2 times x to the -1/2. This is a little messy. We'll have to fix it up a little bit. Well, first of all, the 2 and the 1/2 will cancel. We can ignore those. And x to the -1/2, that's, you should remember, just dividing by the square root. And you don't have to write out all of these steps. There are other ways to simplify this. I just wanted to illustrate. Because when we're dividing by a negative exponent, we're dividing by a fraction. And that means that this will flip to the top when we take the reciprocal of the fraction. So this is actually the square root of x divided by x. And that also reduces, this is x to the 1/2 divided by x to the 1 power. And that's this guy. 1 over the square root of x. What happens to this function as x goes to infinity? What's this limit?
1 over infinity.
Right. So we're going to be plugging in, if we're thinking about this limit, we're thinking about plugging in numbers that get larger and larger down here in the denominator. And a 1 over infinity, what does that come out to? What number should that come out to? If we're dividing 1 by larger and larger numbers?
Zero?
0. Right. So that's the solution here. This limit is actually 0. Okay, so I guess that is a good stopping point for today. Are there any questions here at the end of class about L'Hopital's rule or anything else? Okay, so, okay, and then someone in the chat said that they don't have any questions. Good. So if you don't have any more questions, I will see you guys on Friday morning, and I will get an assignment posted for this section to MyLab Math. And we'll finish this section on Friday, which means your homework won't be due until a little bit later next week.